is energy in bonds, because that's actually a really important thing that we're going to encounter in a variety of different disguises. And so it's important to get it straight. And there's also a common place that people goof up. So that breaking bonds takes energy input. All right? Therefore, it is delta G positive. You have to put energy in. It's not spontaneous. Making bonds so I'm going to start off with a question to talk to your neighbor about. If you remember, so the very end of last lecture, I talked about some rules about delta G, adding things, reversing things, blah, blah, blah. If breaking bonds takes energy input, and why does that make sense? So if I'm bonded to this box over here, my briefcase, right, to pull us apart, it takes some energy. It's like magnets stuck together. A bond is a sticky thing. It takes energy to break it. Okay? If that's true, and you follow the rules for delta G, there's a natural conclusion about what making bonds should be, whether it's delta G minus or plus. So talk to your neighbor, get a consensus. If breaking bonds is delta G plus, what's making bonds gotta be? All right. So think about it, talk to your neighbor, and we'll call a name. We'll get right off the bat start handing out some points. All right, so get a consensus real quick, and I'll pick somebody. Let's see. All right, so Emma, tell me, delta G plus or minus, and how come? Minus, excellent, yes, because? It's cool. The rule to apply is that when you reverse a reaction, you switch the sign of delta G. You don't change the number value, you switch the sign. So if the reaction is breaking us apart, that's delta G plus. The reverse reaction is putting us together. So that's got to be delta G minus. So there's a bunch of ways to look at it. It's symmetrical. It's sort of, they're opposites of each other. Thank you. So making bonds releases energy. Therefore, delta G minus. If you like, and the reason why I do it this way is there are many people that have this misconception that it takes energy to make a bond. And maybe you're picturing sticking pieces together, right? Forcing Lego together to get it to snap together, right? And you need to erase that from your brain, right? That the way to think about it is, I always remember it is breaking a bond, you got to pull it apart. So that means that forming a bond is, they form a bond. They release energy. It's energetically downhill, right? So atoms they're happy to bond, right? There's a lower energy state, right? So for me to always keep it straight, I remembered, you got to go, you got to pull things apart. That's easy to remember. But forming a bond, therefore, is spontaneous. Yes? So if the energy is lost when a bond is made, where does it go? A most excellent question. When I bond, it's a lower energy set. The molecules now have higher energy than this. Lower energy when they're bonded. Where does the energy go? Actually, it turns out once we're bonded, just typically a little bit of heat gets given off. That is, these molecules, when we bond, we're slightly more energetic, and that vibration gets translated to heat later on. So that energy is conserved. The potential chemical energy turns into heat energy. Other questions? All right, so that's a biggie. There are my glasses. All right. So that leads to a very important conclusion, another puzzle I want to give you guys, because this is another thing that's not intuitively obvious, but if you figure it out, it makes total sense. So high and low free energy. So what we know is that, let me do this in color, this is breaking bonds, is delta G plus, moving up the chart. And this is going to be forming bonds. right? There's a conclusion you can draw from that. Therefore, and this is another one I wanted you to talk to your neighbor about. I got 3 states of a system, not bonded at all. So like me and my briefcase here traveling fully separately. So state 1, not bonded at all. State number 2, weakly bonded. So I'm just sort of attached, but not really strongly attached. And then really strongly attached. If you like, not bonded and a single bond and a double bond, right? Or not bonded, a hydrogen bond and a covalent bond. Any way you like. Not bonded, weakly bonded, and strongly bonded. And I want to know on that chart, top to bottom, which one's on the top, the highest energy, medium energy, and lowest energy. So not bonded, weakly bonded, strongly bonded. How do they go in that chart? Based on what we just said up there, it's not obvious, but you can figure it out. So think about it, talk to your neighbor. Those 3 states. All right, so get a consensus, and I'll call a name. All right, let's see. Rose, are you here? Rose. Rose. Rose? Your clicker's here, Rose. Are you? Going once? Going twice? All right. That's unfortunate. Let's try another one. Ezra Bernstein. Ezra, are you here? Ezra. Oh, there you are. Ezra. So tell me, you can go high to low, low to high, whatever you like. Okay, so what's the highest energy situation? I got strongly bonded because it takes more energy to break a stronger bond. All right. I 100% agree with the second part of your statement. But I disagree with the first part. So if it takes a lot of energy to break a stronger bond, then it takes less energy to break a weak bond. Cool. So let's put it, just let's do a pair. Bonded on top or not bonded on top? Let's do, I got a bonded on top, not bonded on top. All right, so how are we going to figure this one out, right? Let me put bonded in the middle, just say, right, so we don't have to worry about it. If I'm breaking bonds, which way am I going? Up. So if bonded is here, where's not bonded compared to my hand, above or below? Above, because you put energy in to break those bonds. You're busting the bonds. So not bonded has got to be higher than bonded. All right? Yeah. Yes, that's a very good way. Another good way to look at it is, let me put it this way, Ezra, so let me thank you for that. So what she said was, you have a stronger bond means you have more energy to bond. That means you fall further when you form the bond. It's more of an not just a sort of an but an right? It's much more dramatic, right? So in that case, who's on the top? Not bonded is going to be way on the top. All right? And who's on the bottom? Strong bonds. Because like what she was saying, it's the farthest, so the strong bond and weakly bonded. And you can look at it either of two ways. The way she said, Not bonded to weakly bonded is kind of like a little bit of an, okay, whatever. And then not bonded to strongly bonded is, a big step down, a lot of energy released. Or, if you got strongly bonded, you got to whack the heck out of it to break it apart. It takes more energy to bust it up than something that's weakly bonded. It takes a lot more energy to break a double bond, say, than a single bond. All right? But that's a really important set of things. Questions about that? Yeah. So it's easy, you'll get more energy out. It's favored for not bonded things to bond. Forming bonds is favored. That's another way to look at it. All right. I have one last conclusion to draw from this. Another therefore. If the bonds of the products are stronger than the bonds of the reactants, delta G, and this is the last, for the moment, the last question I'll torment you with, to talk to your neighbor. If the bonds of the products, what you're turning to, are stronger than the bonds of the reactants, what's the sign of delta G? Take a second and talk about that with your neighbor. The last of these delta G puzzles, right? So so the bonds of the products are stronger than the bonds of the reactants. Products are the end, reactants are the start. So you're going to stronger bonds. What's it mean about delta G? So think about it. Talk to your neighbor. We'll do it, and we want a sign on the of delta G. All right, so a consensus, it's sort of a 50-50 shot, but I know we can do better than that. And then I'll call a name. All right, Sophia. It'll be negative because why? Because the products are more... Exactly. What you're doing is going from weak bonds to strong bonds, which is delta G negative, right? So you're moving down the chart. So Sophia's got it exactly right. Delta G negative. Therefore, it's spontaneous. So what does that mean? It means the bonds in graphite are stronger than the bonds in diamond, because spontaneously diamonds goes to graphite. It means the bonds in the products, carbon dioxide, water, all that stuff of TNT are stronger than the bonds in TNT. So TNT is a weakly bonded molecule. It is unstable. It is weakly bonded. That's what makes it explosive. It's got lots of weak bonds. Those atoms would rather be bonded in a much stronger way than they are in TNT. Yeah? That's a really good question. If the bonds in graphite are stronger, why is it softer? Because it turns out the bonds in graphite put the atoms in flat sheets that slide over each other, whereas in diamond they're actually cross-linked in 3D. So it's actually not just the strength of the bonds, but it's the way the structure is actually built. Yeah? No, is that why diamonds last longer than graphite? Technically, graphite should last longer. Eventually all your diamonds will turn to graphite if you wait long enough. But long enough means like since the dinosaurs have been around. Right? All right. So that's another big deal. All right, fine. Let us now apply some of this in a variety of ways. Or actually, I'm going to put that aside and talk about